Dear Honorability, Spectrabilis, dear colleagues. First of all, let me introduce myself. My name is Dominik Ročka and I'm the Vice Chairman of the Academic Senate of the Faculty of Natural Sciences of Comenius University in Bratislava for student part. It is an honor for me to welcome you in the name of Scientific and Organizational Committee at 51st Student Scientific Conference of the Faculty of Natural Sciences of Comenius University, which is unique of its kind in the conditions of Slovak Republic. It represents a significant part of scientific knowledge dissemination throughout the faculty, heightens the attractiveness of studying at the faculty, and also has a great importance for the faculty management, guarantors of study programs, teachers, and researchers working at the faculty. The conference presents scientific papers from various scientific fields, from biology through chemistry, geology, geography, environmental studies to didactics in science. Students of all three degrees of study acquire in the auditorium with the results of their work, not only from Slovak, but also from foreign universities, research institutes, and other scientific workplaces. Authors as well as auditors gain practical experience in formulating conclusions and generalizing the results of research work. They have the opportunity to present themselves and their scientific work. Also, they get an overview of research in various scientific workplaces. Unfortunately, as it happens in the winter semester, this year's pandemic situation forced us to transfer the conference to the virtual world. But it did not reduce the level of either professional assessment or organization implementation. The Student Scientific Conference of Faculty of Natural Sciences of Comenius University in Bratislava is under auspices of Rector of Comenius University in Bratislava, Professor Števček, and Dean of Faculty of Natural Sciences, Comenius University in Bratislava, Professor Fedor. Now, I would like to ask for introductory speech, Vice Rector for Education, Dr. Kovačičová, for introductory speech.
Thank you very much. Dear Mr. Dean of Faculty of Natural Sciences, dear past participants of Student Scientific Conference of Faculty of Natural Sciences, dear members of Organizing Committee, dear university teachers, and all of you in the stream. It's my pleasure and honor to participate in such a distinguished and influential event. On behalf of Rector of Comenius University in Bratislava, I would like to thank you and thank the Faculty of Natural Sciences for organizing of such important every year event, even online today during this pandemic time. The mission of our university is to offer the science-based education, and this scientific conference is a great contribution to meet it. Dear students, dear presenters, the day is here, the floors are yours, and the performances of your scientific projects and results are beginning. I wish your participation and your papers will make the conference an inspiring, exciting, and joyful event. I would like to congratulate all of you for your participation. All of you are the winners even before your presentations. As the students, you win the possibility to work in open-minded national or international scientific teams, to contribute in finding the answers to the research questions. You are really science and learning-oriented students. You are the young scientists and ambassadors of the positive approach to the science. Your enthusiasm, effort, and knowledge are the important contribution to understanding among scientists and others, which is currently very important. All your results are admirable, but I would like to emphasize the role of your teams and especially the role of your teachers who have contributed a great deal to your projects. I would like to thank you to all teachers. Many of them are our university colleagues for their hard work and extra time they have put in. Some of them already passed away, but their light is living in you, their students. I wish you a successful scientific conference, fruitful discussion, and something very important, your good feeling for the well done good job. Thank you all for coming. Thank you.
Dear Honorability, thank you for your speech. It was very inspiring. And now I would like to ask the Dean of the Faculty of Natural Sciences, Comenius University in Bratislava, Professor Fedor, for next speak.
Oh, thank you very much, dear Vice Rector, ma'am, colleagues, professors, associate and assistant professor. But first of all, dear students and all academic staff, ladies and gentlemen. Exploring nature, its origin, history, dynamics from basic chemical substances, cells and tissues to whole organisms, complex ecological systems, sometimes appears like building a card pyramid. You know what I'm talking about? Quick moves may be disastrous, especially if you were to breathe too hard. So generally speaking, natural history is a clear and simple concept, but its specific and particular details are much more difficult to understand. I'm very pleased to have this opportunity to say a few words at the opening ceremony of the student conference. And it's a big honor and my deep pleasure to welcome you to the Faculty of Natural Sciences, one of the best and most reputable faculties of Comenius University, with its 5 basic sections from chemistry, biology to environmental sciences, geology, geography, with almost 3,000 students and 400 members of academic staff. In fact, especially you from the other universities and institutes are visiting this faculty just shortly before a general reconstruction, monumental project for almost 30 million euros. So when you visit this institution in a couple of years, maybe the next year in some time, it will be a big pleasure to welcome you in an absolutely new institution, absolutely new building. You know, the COVID-19 pandemic, which has been sweeping across Europe, has made changes to many phases of life, from working conditions to freedom of movement. And education has been one of the sectors disrupted by crisis, with educational provision, both in Europe and globally, going online. When the COVID-19 pandemic began, natural science digital learning tools became a critical need overnight. And the shift to emergency distance learning forced educators to quickly evolve and stand up new technologies to keep students learning, often taking a trial and error approach. As we have all witnessed, this shift wasn't without monumental challenges, and in some cases created learning gaps for students. Many students and teachers have discovered that this crisis distance learning model in chemistry, biology, and other natural sciences doesn't work perfectly for them. Can you imagine chemical experiments without typical smell, and sometimes due to voice connection without camera? But you know what? The best and talented natural science students like you are undisputedly possess an ability to remain perfect despite this pandemic. And this is why we finally organized this event. So once again, many thanks for joining us, and good luck to be the best, because you are the best students and best talented. And before we get started, I would like to express my sincere appreciation to all of you who generously helped to make this event come together to become a success. The whole team of Dr. Eva Biglashova from the Department of Nuclear Chemistry, we couldn't have done it without you. Thank you very much. And once again, welcome to Faculty of Natural Sciences. Thank you very much.
Respectfully, thank you very much for your speech. And now, without any other further hesitation, periodic table. Dr. Pašteku currently works at Comenius University at Faculty of Natural Science and Department of Physical and Theoretical Chemistry. Beforehand, as a postdoc, he worked at Massey University in Auckland, New Zealand. His work focuses mainly on research on relativistic effects, modeling, and prediction of properties and actions of organic elements. Collaboration with researchers from University of Auckland and Sydney. He tried to design and aim experiments to find new physics. Respectability for your speech, and now, without further hesitation, we will move to the next presentation of my lecture, Mr. Pašteku. Topic: Are we now this periodic table?
Okay, hello. I'm not sure whether this was my cue because I couldn't hear Dominic, but I assume it is. Okay. So good morning and thank you for the introduction. I hope you can hear me well. I had some problems with my sound, so let me know if something's wrong. So thank you for the introduction again, and of course thank you for the opportunity to speak here today in general. I appreciate it very much. So in my talk, I will be looking at the periodic table of elements, something everybody is fully familiar with. I hope the slides. Okay. Right. Okay. Now it seems to be working. All right. I'm trying to change the slides, but it wouldn't change. Even though
you have to double click. Try
double click. Okay. All right. Okay, now it works. Thanks. All right. So yes, as I said, I will be talking about the periodic table of elements. That's something that every one of us has seen in the high school classroom and should be quite familiar with. The periodic table currently is roughly 150 years old. Well, roughly it's a little bit more than that because in 2019 we celebrated this anniversary as International Year of the Periodic Table of Chemical Elements. So I understand I'm a bit late to this game, but I still hope that you will enjoy my talk regardless. So what I will focus on is where we are now at this moment with the periodic table, how we got here, what lies in the future ahead of us regarding the periodic table, and can we get actually fun and creative about the periodic table. So let's start with the periodic table itself so that we all know what we are talking about. This is it. This is the current version of the periodic table that we currently have with all 118 elements. Typically, it would be arranged like this to save some space, but the other arrangement also is quite important, and I will get to that later. So let's do a quick refresher about the whole idea of the periodic table. Why is it arranged like this? Because if we get elements, we can basically put them in an order or a list just by their mass, atomic mass, or their proton number, or proton number equals the number of electrons as well. And this is very convenient measure because it just goes as 1, 2, 3, 4, 5, and so on, up to currently 118. So why not just keep it as a list? Well, it is a pretty scientific and systematic idea, right? And in fact, it is a first step to getting to the real periodic table as we know it now. So if we arrange them by their atomic number or proton number and try to look at some other property of these elements as correlated with the atomic number, we can observe some peculiar repetition. One could even say periodic pattern. So that's where the period comes from. You can see here that there are there are these sudden jumps in this property. So this property current is the radius of the atom as a function of the atomic number. And you see these sudden jumps, and these highlighted elements are always on top. These other elements are always on the bottom, even though in our original list they are neighbors to one another. So what's going on? It suggests that these sudden jumps should be useful line breaks for our periodic table or for our list. This also happens for other properties. So this is an example of ionization energy of all the elements, or not all, but up until 86 radon. And as you can see, this is a similar trend with a similarly repeating pattern. It's just flipped upside down. So the elements which were on the top on the left are now at the bottom, and the ones that were on at the bottom on the left plot are now at the top. And the pattern is sort of flipped, but it's still there. So if we now use these jumps as our line breaks, we arrive at the structure that looks like our periodic table as we know it. And the elements which were highlighted here are now highlighted here as well, and they form columns in this table. And these columns are called groups, as you know, and each group has a certain name. So these would be alkali metals, and these are noble gases. And each group shares some sort of property or similarity in multiple properties across this group. So this is quite useful that we now have groups. This also applies not only to the leftmost and the rightmost group, but all the other groups in the periodic table. So we have columns which are called groups, and then the rows are called periods because the properties are periodically repeating, as I said. So now if we plot any property we like we did for the atomic radius and the ionization energy in the previous plots, now if we put them in 3D into the table format, excuse me, we can see the trends more clearly. So there's smooth increase in one direction or the other direction, depending on the property. And this also works not only for these two properties that we've already seen, but for many others. These are examples of electronegativity and electron affinity. So that's the likelihood of an atom to attach another electron to it. And in these properties, especially here on this plot, you can see more structure than you could see here. You can see further jumps or gaps, which are located between these different colored blocks. And these blocks are called S, P, D, and F block. So if we go back to our original table, these four blocks are colored as such. So this is the S block, the P block, D, and F block. They also have other names. These labels come from history. They don't make much sense anymore. They stand for sharp, principal, diffuse, and fundamental. But now we only stick to these labels as a single letter. And the block, each block is related to the underlying electronic structure of the elements which are in the block. And these are represented by the valence orbital. As you can see, the shape of the orbital becomes more and more complicated as you go from S, P, D to F. It has more and more lobes. Okay, so let's go back to our table. All right, so if we apply this exercise, we arrive at this shape of the table. This is why it looks like it as you see it now. But the periodic table wasn't always looking like this. In fact, very recently it was still evolving. So not so long ago, in your classrooms, probably you could have seen periodic tables that looked like this, or especially if the students come from Slovakia, they should be intimately familiar with this one or some version of it, which almost every millennial student was carrying around in their chemistry notebook. So what's different from the periodic table that I showed you before? The differences are mostly located at the tail end, at the 7th period, the very end of the periodic table. You can notice that these are quite different. There are gaps, there are missing elements, and there are also missing names replaced by these weird 3-letter symbols like unununium and so on, which are just translations of the number of the element. And also you can notice that all of these differences or nuances are highlighted in yellow in this table, which maybe you can see it here, stand for artificial elements. So the natural elements seem pretty stable, but the artificial ones were changing until very recently quite a lot. If we go even further down in history, now we see a different periodic table, which is from 1925, but most of the periodic tables of that era look similar from the turn of the century. You would see, we shouldn't be thrown off by the fact that the noble gases are located at the leftmost column now, but it doesn't matter, that's just cosmetics, and the lanthanides are in the middle here. That's just cosmetics. What I mean, what I'm mostly concerned about are these gaps in somewhere in the middle of the periodic table at 43, 61, 75, and 85. And also the fact that it ends at 92, uranium. There's no elements beyond. This is quite typical of all the periodic tables of that era. The reason was these were the known naturally occurring elements, and all the yellow ones could not be created because up until then researchers only relied on looking for elements which are present in nature. They could only discover them, not make them. So then, yeah, there were these gaps typically, but then came Ernest Lawrence with his new toy, the cyclotron. This was originally this was a pocket-size accelerator, which was based on a clever principle of static magnetic field and oscillating electric field, and it was capable of accelerating a charged particle traveling in a spiral outwards from inside to very high speeds in a relatively compact size system. So this was a big game changer. So let's look what happened next. Let's look at the timeline. So as I said, before 1930, we had these periodic tables which were missing a lot of things. And then yeah, then we had all these discoveries in the previous century and this century as well. So at the beginning, Italians begged Lorentz for parts of his equipment, and they discovered elements technetium and astatine in these parts. And Lorentz then also focused on discovering new elements beyond the missing gaps, which were 43, Z43 and Z85 for these two elements. There's also promethium later on, which was found by Americans. So in a rapid succession in the 1940s and early 50s, the Americans at Berkeley lab discovered most of the transuranium actinides up until the element 101, which mendelevium, which is here. And then there was a big gap. For a while, they couldn't find more things, but they were still working on it quite a lot. Also, Russians joined the game, and they were also studying similar things. They built their own cyclotrons, but surprise, surprise, at that time they didn't talk to one another very much. So they were mostly working in parallel and discovering elements independently. So that's why they have these shared discoveries between US and Russia. Then again, there was a gap for a while. So after these four elements were discovered, then came this guy, Yuri Oganessian, here on this picture, and he invented a new technique called cold fusion, which is not the cold fusion that was debunked. That's a different story. This is a cold fusion of target bombarding elements, lighter elements to produce more heavier elements. And with this technique, in the following decades, they discovered these elements up until between 106 and 112, which is copernicium. These were mostly done by the German team in collaboration with Yuri Oganessian and the Russian team in Dubna. And then Yuri Oganessian again saved the day by tweaking his methodology and coming up with the so-called hot fusion, which then was able to produce even heavier elements, which rounded nicely the table at 118, and he received eternal glory by placing his own name in the periodic table of elements. Or, well, he didn't place his name there, but yeah, he is there. He deserves it. I'm not saying otherwise. All right, so I only mentioned countries, but it would be fair to mention the actual labs. So these are the key players of this game of making new elements. The first who started it was the Lorentz labs in Berkeley, California, and then later the Research Institute in Dubna, Russia, and then Darmstadt, Germany, Japan, and finally also another team in the US in Tennessee. Perhaps these names of the laboratories sound familiar. It's not a coincidence, of course. They all wanted to leave their mark on the periodic table, so to speak. So the Lorentz labs gave us Lawrencium, and they were located in Livermore and Berkeley. So we got Livermorium and Berkelium, which both of these are in California, bam, United States of America. So they left quite a big mark there. Similarly, the researchers from Dubna, which is very near Moscow, left their mark there. Same story with Darmstadt in the Hessia region in Germany, Hessen. Japanese researchers didn't use the English name, but used the Japanese name for their country, which is Nihon or Nippon, depending on the pronunciation or region. But so the element is called nihonium based on that. And then the Tennessee lab also has their tennessine. Right, and the other elements which were not named after places or labs are named after people. So as soon as you run out of Greek gods and Roman gods and Nordic gods like thorium for the element like thorium and neptunium, plutonium, and so on, uranium, you start with the gods of science. So you get Marie Curie, the goddess of radiology, or well, not radiology, sorry, radioactivity. Einstein, the father of relativity. Enrico Fermi constructed the first nuclear reactor. Yeah, who could forget Dmitry Mendeleev, whose idea started this whole thing. Then Alfred Nobel, the boom guy. Ernst Lawrence, as we mentioned. So this is sort of a dual. So it's the place was named after a person. So it's hard to say whether the element is named after a place or a person. It's sort of both. Then we have Rutherford, who discovered the atomic nucleus. Niels Bohr, one of the founding fathers who laid down the foundations of quantum mechanics. Lise Meitner, who discovered nuclear fission. Röntgen, who had his X-ray vision. Copernicus doesn't even need an introduction. And Georgy Flerov, who probably is the least known of these, but is the famous Russian nuclear physicist. And then there are these two gentlemen who were the only people in history who actually got to see their name embedded in the periodic table while they were still alive. So Glenn Seaborg was the director of the Berkeley lab for a long time and participated directly on the discoveries of many of the elements. And he passed away in 1999. On the other hand, Yuri Oganessian, who worked together with the Russian team and the German team and was directly responsible for many of the discoveries, he's still alive and well and kicking. And he's currently the only living person who has their name in the periodic table. And he's very likely to remain the last one as well, because later IUPAC banned the practice of naming elements after living people. So you shouldn't get your hopes up. If you go to super heavy element research, you probably won't get your name or in the periodic table, or at least you won't see it. You can get it there after you pass away. Right. Okay, so how do they do it? So the practice is based on the original cyclotron idea, which you can see here with this spiral, which resembles the original sketch of Lorentz. But his cyclotron was much smaller, so naturally things get more complicated and bigger as you progress in research. These are really complicated, heavy machines, very costly. But the idea and the principle is still the same. So you take a light element and you strip it of all electrons, and you accelerate it in the cyclotron to very, very high speeds and smash it into a target of a heavier element. So as an example, we have the lighter element, which is accelerated calcium-48 and californium-249, which is the target element. So you smash these two together, and then you just hope for the best. That's all you can do. So in some rare occasions, the conditions are just right, so that the two nuclei merge together instead of just splitting into smithereens. And if they do, then you produced a new element. So that's one thing. But then you have to prove that you have a new element there. So how do you do it? Usually these new elements are very unstable, and they only survive for few milliseconds in this case of organeson, and they decay. And from the decay chain, you actually can observe this decay chain. You can see the escaping alpha particles and the remaining isotopes that are a little bit more stable, or at some point it will arrive at a stable configuration, and you can trace it back all the way to the original element. So you can indirectly prove that what you produced was indeed a new element. And if you do this sufficiently often, then you can claim a discovery. So if it's reproducible. Ideally, if two different labs do the same thing and they produce it, and you can confirm that this is the same thing. Right. Okay, so as I said, these events happen very rarely. So you produce actually one atom at a time of these super heavy elements. So of these elements in the last row, for all of them, less than 100 atoms was produced in total. For many of them, less than 10 atoms was produced, which is insane considering how much effort and how much money they actually pour into it and how much time. It is exciting, but it's difficult. And now when you produce those elements, they are all unstable. So there are no stable or metastable isotopes which would survive for a little while that you can actually do something with them. And they fall apart pretty quickly, usually in the range between microseconds and minutes. The stable super heavy elements require more neutrons. That's the big problem of this, because if you look at this chart of the stable isotopes, which are represented by these black dots, you can see the curves away from the Z equals N, so the same number of protons and neutrons which are found in the lighter elements. That's not the case. For the heavier elements, you need more and more neutrons to actually make those nuclei stable. Otherwise, they fall apart. And since this curves away, if you take elements from this part to make elements which are here, you always end up in a neutron poor isotope. And that's why they are unstable. So this is a big challenge to figure out a way how to produce elements which would be more neutron rich. Because it's expected that the more neutron rich isotopes would be much more stable. All right. So I actually tried to calculate how much does it cost to produce a gram of some of these elements. So the lower bound, I was very critical, and I really tried to not overestimate the costs, but rather underestimate everything I could. And the lower bound that I found was 10 to the 27 US$ per gram of either of the super heavy elements. So that's an octillion dollars, which is insane. You often hear that the most expensive substance that is produced is the antimatter, but anti-hydrogen costs only $60 trillion per gram. So that's nothing compared to the super heavy elements. Okay, but the machines are built, they are running, and they will be running for a while, so the show must go on. So they shouldn't scrap that. They are now looking for elements 119 and 120. And I guess you will admit that the current names ununanium and unbenylium are quite weird. Who wants them? So we should better discover them and name them properly. About the neutron-rich and neutron-poor problem, there's this thing. It's sort of like a mythical thing in nuclear chemistry, nuclear physics, sorry, where people are searching for the so-called island of stability. So you can predict which proportions of protons and neutrons should be stable, and the island of stability should be somewhere here. And we are currently on the left side of it with all these super heavy elements. So the gray squares represent the isotopes which were already observed. And as you notice, all of them are on the left side, which means they are neutron poor. But if you also look at the trend of the isotopes, the multiple isotopes of flerovium that were observed, you can see that there is an increase in the direction towards the mythical island of stability. So there's probably something to it. It's not based on nothing, of course. It's based on quite rigorous theory of nuclear structure. So it's not a total fable, but the problem is how to make these elements stable. So if the researchers actually produce these, they expect that they would be at least relatively much more stable than the ones that we've already observed. This doesn't mean that they would be fully stable, that they would not decay at all, but their lifetimes should increase quite a lot. So here you see an increase of 3 orders of magnitudes. If you go further this way, then maybe you get to hours or days or maybe something like this. So this is not the only island of stability, but it is the closest one that we are trying to reach. Then, of course, there's another one at the proton number of 126, and then another one around proton number of 164. But those are too far away at the moment. Okay, so now there's a cheaper alternative to all these heavy machines and this big stuff. And that's this. I guess you've already seen a computer. You can actually mimic or simulate all of the peculiarities of the super heavy elements on a computer without actually having any atoms of the super heavy element at all. The only thing you need to feed the computer is quantum mechanics. This is also, so if you join these together, you write some programs, then you use those programs and you calculate stuff. This is called quantum chemistry or quantum physics as well. So they use similar principles, but in my case it's quantum chemistry, and that's what I'm doing. And I would just use Richard Feynman's famous quote: "What I cannot compute, I cannot understand," which I think really nicely summarizes this. So even if we have those elements and we observe some properties, but to interpret these properties, we can still use theory and theoretical methods to be able to explain things much more clearly, because otherwise, without the theory, it's just guesswork. All right, there's a little bit of a complication though with the super heavy elements, and that's relativity. The problem is that the heavy nuclei are so much charged. The charge of the heavy nucleus is so big that the surrounding electrons have to travel very, very fast in order not to fall in. and their speeds are kind of comparable to light speeds. They're not approaching light speeds completely, but they are a non-negligible fraction of light speed. And that changes the properties of the electrons. So the electrons become effectively heavier because they travel so fast that you can actually measure how heavy they are. It shrinks the orbitals and it changes a lot of things. And you have to take this into account. So this guy also comes into play. And we have to somehow merge the ordinary Schrödinger style quantum mechanics with special relativity of Albert Einstein. And this is done by the Dirac theory. The relativistic effects, what they do also is breaking trends. So if we come back to the examples that we saw before, for the ionization energies and electron affinities of alkaline metals or alkaline earth metals, both of these show a very nice downward trend. But then relativity kicks in as soon as you reach francium, radium, which are heavy, and then if you go super heavy, the relativity spikes up even more, and then the trend is reversed. So it's not a negligible thing. You actually have to take it into account. It's very important. Many chemical relativistic effects can be actually observed in real life by our own eyes, and you know them. Maybe you don't know they are relativistic, but you've seen those things. So the prime example is the yellow color of gold. This can be simulated. So on a computer you can turn the relativity on and off. You cannot do this in the real world. This is another advantage of the computer, that you can do this, and if you do it, you can actually observe a difference in the absorption spectrum of 1.6 eV, which translates to around 200 nanometers difference in the absorption spectrum. And this pushes the gold absorption into the visible region, and now the gold absorbs blue and violet light, so the complementary color is yellow, and that's why it appears yellow. If there was no relativity, or if we switch it off on the computer, the gold would look just like silver here. Another famous effect is the liquid state of mercury. So you can again simulate the melting of mercury with and without relativity. So this is no relativity. Here you have relativity, and you can see a difference of over 100 degrees in the melting point, which brings it low enough so that it's liquid at room temperature. And the third very good example is the lead acid battery, which is a very practical thing for everyday use. If you do a relativistic versus non-relativistic calculation of all the different parts and the energy of formations of the different constituents of the reaction, you'll see very big shifts, and you can calculate that the nominal voltage, which is 2.11 volts, 1.7 volts of that is only due to relativity. So without relativity, it would be less than 0.4 volts, and your car just wouldn't start. Right, so these are the things we model. You probably noticed that all these three examples are heavy elements. So they're gold, mercury, and lead are here, and not the lowest row, but one above. But if you apply the same methodology on the row below, on the super heavy elements, you can also calculate properties of these elements, even if you don't have them in a flask. So you can essentially predict their properties even before we make them. And some of the things I will just illustrate here, some of the things I participated on, but not all of them, but I mean collective we as we researchers, humanity. So we discovered that the oganesson, although it's in the group of noble gases, is not noble at all. It's not even a gas anymore. At room temperature, it would be solid. And furthermore, it's a semiconductor. So this is quite weird. So it's not noble, it has even positive electron affinity. So it creates an anion, which none of the other noble gases want to do. So they are perfectly happy with their closed octet. They don't want any more electrons, but organeson does. And another example would be copernicium. So if we freeze it down, we know what the crystal structure would be like. It would be the hexagonal closed pack structure. But at room temperature, copernicium would be liquid. Copernicium and flerovium are both actually much more noble than organeson is, even though they are D and P block elements. But they have the stability of their closed shells is much higher than that of organeson. And it's also exhibited by the fact that it's a liquid at the room temperature, which is only the third liquid element in the periodic table after bromine and mercury. So this is just to illustrate how things are simulated for organeson and the melting point. So you would take this box where you have part of the organeson atoms arranged in a crystal lattice and part of it is disordered, so that's liquid. And this box is periodically infinitely big, so it repeats in all directions. And then you tweak the temperature on the computer in your simulation, and you watch whether it completely freezes over or completely melts. And you squeeze from both sides until you find your correct melting temperature when there is a equilibrium between the two phases. And if you do this, you actually see how much does the relativity break the periodic trends that we love so much. So for all the other noble gases, the melting point is very low, very much below zero. But for organeson, it's much higher. So I didn't even plot this because it would shoot off too much. So instead, you have a table. All right. Okay, so we arrived at 118. So organeson was my last example, but that's not the end, at least not for the computer. So you can put elements which are beyond 118 on the computer. You can calculate those as well. So you can calculate these fictitious elements or virtual elements so far. They haven't been produced, but you can already make chemistry with them on a computer. You can predict their properties. There's also, so you have a new row, which would be the eighth period. There's also something missing here, which is completely new, and those are the G elements, the new block, G block. I will go to the long periodic table so that you can actually see where it fits. So the G block is somewhere here, or not somewhere, it should be directly there, which is good news because it's right around the corner. So if the elements 119 and 120 are produced soon, then what's next are the G elements, which are completely new with completely new properties. That's something that we have no parallel for in the current periodic table. So that's quite exciting. Of course, as I said before, these blocks are related to the electronic structure, and there was an increase in complexity of the shapes of the orbitals as you go from S to P to D to F. And then the G block, which doesn't stand for anything, it's just the continuation of alphabet at this stage. So if there were more elements, then there would be an H, I, J, and so on. But G is currently the next one, and you see the complexity increases even more. So there are more lobes, and there's more of them than there are F and D and S and P. So there's always an increase in complexity. He also noticed one more thing, that this periodic table ends here at 173. This isn't just my laziness or that I didn't continue this further. This is not an accident, it's the limit. So there actually is a limit to the periodic table, not dictated by the nuclear structure. So if we got all our stable isotopes that we wish around whichever island of stability, and if we got those nuclei, we still couldn't form new elements because the electronic structure just doesn't work after this point. And the reason is, I don't want to go into too much details, but if you look at the 1s orbital energy of hydrogen-like atoms, and you increase the nuclear charge and you go up and up and up, the energy goes down. This is natural, this is expected, that's fine. But at some point it dives into the so-called negative energy continuum, and then it totally breaks down. Then no more elements can be formed beyond this point. Where this point is sort of depends on the isotope, and it depends on the nuclear structure a little, on the model as well, but it's somewhere between 171 and 173. So that's the critical charge. If you haven't heard of the negative energy continuum, that's okay. It's just the result of the relativistic quantum theory, which is governed by the Dirac equation. You wouldn't see a counterpart of it in the ordinary Schrödinger theory. So this is a purely relativistic thing, but this is the continuum which contains positrons, so the anti-electrons. That's also why it's expected that if this happens, if we had a nucleus, which would be somewhere here, it would cause a spontaneous emission of pairs of positrons and electrons, and no more electrons could be bound to the nucleus. Okay, another fairly interesting question is what elements can be found elsewhere in the universe? Like, we're still trying here on Earth, we have our small measly machines, but compared to what's going on in the universe, what kind of machinery of stars is out there? Can we expect that there would be something found somewhere else which we couldn't see here, like in the sci-fi movie? What we can use for this is a quasar. Quasar is a very hot galactic center which eats a lot of mass and spews out a ray of particles which can travel across the entire visible universe. And if we are lucky, one of these rays actually aims at our Earth. And on the path from the quasar to Earth, there's some nebula or other galaxy or something. And then it actually sends out a spectrum to the Earth, because this cloud absorbs part of the light that comes from the quasar. So you see an ordinary spectrum with these spectral lines like you do on Earth. And you can say something about the corner of the universe where the spectrum came from. So you can compare the spectrum that you measured from your telescope to the spectrum that you measured in your lab. And you can even calculate the spectrum, which should match the one that you found in your lab. But you can, on the computer, as we said, you can do things which you cannot do in the lab, and that's you can tweak the parameters of the simulation. And the parameters of the simulations are fundamental constants. So you can actually move fundamental constants around and deduce whether in a distant part of the universe there is a different set of fundamental constants. And from there you can deduce whether there are different elements as well. So if there are different physics, there would be different elements. And indeed, there is something there. So people actually compared all the quasar spectra that were ever measured from around all the globes and all the telescopes. And they found it's a noisy correlation, but there is some sort of a correlation across the visible universe. There is a gradient in the value of alpha, but the gradient is not very big. It's 10 to the minus 5. But it suggests, I'm not getting into what alpha is, it's related to the speed of light. But it suggests that there's different physics in the different parts of the universe, at least slightly different. How slightly? I can illustrate. So if we actually travel across this gradient, we would notice changes on the 18th digit. So this would be the order of the change of the constants that we see. So something over here. Usually the precision that we can measure to is much lower than this, so we cannot actually observe this. This wasn't ever confirmed by the terrestrial measurements. At least not so far. But it also means that for all practical purposes, the entire visible universe is the same. So aliens don't have different elements as we do. So there's nothing special, at least in the observable universe. So and only regarding to the composition of elements. So they have the same periodic table, but they can still have different chemistry. We actually rely on the fact that the laws of physics don't change across universe too much in all our astronomical observations. But I wanted to say that the chemistry in different corners of the universe can be different because there are very extreme conditions, like in the pressures of the centers of the planets are really, really high, which can squeeze atoms together to form metallic hydrogen, or any element becomes metallic if you squeeze it hard enough. Then there are also very hot temperatures, of course, like centers of the stars are very hot. The surface of a star is a little bit less hot, but still quite hot. And in the corona, there's some chemistry going on. So it's not only nuclear reactions that are going on on stars, it's also a little bit of a chemistry which cannot be reproduced here in the lab. And the specific case are neutron stars or white dwarfs or so-called magnetars, which have very, very strong magnetic fields, which overpower the electric fields present anywhere. So if we have an electromagnetic force, the magnetic part of the force is usually really tiny. No one cares about it. The electric part is much stronger. But on these neutron stars, they have an atmosphere which is a few micrometers thick, which is a stretch to call it an atmosphere, but it is there. And you can actually observe chemistry there. And this chemistry is completely weird. So you can get bonds between carbon and hydrogen, like one carbon can bond to 10 hydrogens and can form a star. So everything is sort of flattened out, and you would form these multiple bonds, unlike anything you can do here. But you can model this on a computer as well. Then I also wanted to mention that we can look at what the atoms that we have, and can we actually tweak them, and can we get creative, and can we build exotic ones. So the ordinary hydrogen is this. Of course, the proton consists of some gluons and quarks, and we can take the physicist's periodic table, which contains all the elementary particles, and try to replace some of these things here with other things here. The only thing we have to take care of is the total charge. So if you want to replace electron, you have to replace it with something negative. If you want to replace proton, you have to replace it with something positive, and so on. So the total charge of the system should be 0, so to get a neutral atom similar to hydrogen. So we can do things like this. So this is our stencil, which is the hydrogen atom. But then we can swap the electron for muon, which is a cousin of an electron, which is 200 times heavier than electron. And so you keep the proton, you chuck in muon, and what you get is an atom which is much, much smaller. So the muonic cloud is much more compact because of the mass of the muon. So now you have a completely new element, so muonic hydrogen. You can combine electrons and muons as well. And people actually do it, and you can actually make molecules out of it. But the problem is it's very unstable, and it only lasts for a few microseconds because the muon itself is unstable and it decays. Then you can do the other thing. So you can replace proton here by something positive, which can be positron. So that's the anti-electron, the antimatter cousin of electron. Then you get something, so they have equal sizes, so it's not like one orbits the other, but they orbit a center which is somewhere in the middle. But this is also unstable. It lasts even less than muonic hydrogen because these two are antimatter particles, and as you probably know, they can crash and annihilate. And then you can replace both parts with their antiparticles, and you can just essentially swap plus for a minus in the hydrogen, and you get an anti-hydrogen. And this is stable as long as you don't touch it. The charge is symmetric, so the particles themselves are stable, and the whole system is stable. You just cannot touch it because as soon as matter touches antimatter, it annihilates. But you can keep it in a magnetic field or a trap, and you can keep it for very long because it's stable. As I said, it's dirt cheap compared to the super heavy elements, so only $60 trillion per gram. There's an interesting question tied to anti-hydrogen, what people are trying to use it for. They actually take anti-hydrogen atom, cool it down so that it's basically motionless, and then they let it drop. So people want to see whether antimatter actually falls down or falls up. Everybody expects that it falls down, but it hasn't been ever confirmed experimentally. So people are actually trying to confirm this and to finalize this question. But it is an interesting question. Right, so if we go back to our ordinary table, we can also reduce the table by reducing the number of dimensions of our universe. So if we do if we live in a two-dimensional universe, the periodic table would look something like this. And you can actually, this is one of the things you can also do on a computer. You can also go to four dimensions, but it's less neat. This is much nicer. The thing you can observe is you have fewer elements there, so some of them are skipped, at least in the paper that they named them, so they skipped carbon, sorry. And trends are somewhat similar. The missing elements are just interpolated, but the trends are more sharp. So it's bigger at the beginning and it's smaller at the end compared to the dotted line, which is the 3D, which is much more flatter. So here you have a much larger downward trend. And the atoms are smaller compared to the 3D partners. And you can also go to 1D. Now the problem is the periodic table is now extremely simple. So you have only alkali metals and noble gases. That's it, nothing else. And it's also interesting, you can form molecules out of these, but since this is only in one dimension on a line, the electron cannot get from one side to another. So all your wave functions are located on either on one side or the other side. And it matters where you put your electrons. So if you form a molecule, if you have two hydrogens, 1D hydrogens, and you put your electron on the side or in the middle, they have different different properties. And here, 2-electron system, dihydrogen, same thing again. So 1 electron in the middle, 1 on the side is the most stable configuration. All the other ones are unstable and fall apart. All right, so these are all the fancy things that I wanted to talk about. I hope you found it interesting, and if you did, please just ask whatever you wish to ask.
Thank you very much for your presentation. It was very inspiring and beneficial for me, and also for others, I think. I'm very sorry for the technical difficulties we experienced before.
That's fine.
I will tell something about you right now. Dr. Pašteku currently works at Comenius University Faculty of Natural Sciences at the Department of Physical and Theoretical Chemistry. Beforehand, as a postdoc, he worked at Massey University in Auckland, New Zealand. In collaboration with researchers from the University of Groningen, Auckland, and Sydney, he tried to design and aim experiments to find new physics, like beyond the standard of model of physics, such as changes in values of fundamental constants in time and space, or detection of dark matter. In addition to research and learning, he is involved in popularizing science and activities aimed at supporting talented students. So thank you once again for your presentation. We have some questions. So maybe I will take the first question for me. Back in the presentation, when you mentioned the 4 blocks like SPDF, I noticed that the helium is not assigned to any block. Why is that?
It's only formally so. It is in the S block, but since its properties are very similar to noble gases, it's usually shifted to the very right of the table, but it should be in the S block.
Okay. We have a next question from the Facebook. Is there some proof that periodic table at another planet than Earth is, and not with the uranium-92, but with the element with higher atomic number?
No, at least, as I said, not within the observable universe. No, there's no proof, and probably won't ever be one. So we don't know what's beyond the observable universe, how big it is, if it's infinite or not. If it is, and if there are different physics in different corners, very far, then it could be possible, but it's out of our reach.
Maybe next question, is there also observable relativistic effect in the bromine? It's also liquid, like you said.
Yes, this is not entirely due to relativistic effects, but it is part of it. Yes, it would be liquid. It would shift if you switch off the relativity. The melting point would shift because it's heavy enough to actually sense the relativistic effects, but it wouldn't be. It still would be a liquid.
We have a next question from I'm not a chemist. Is there a limit of the creation of super heavy elements you think the scientists will not be able to get over? And if the element exists only for milliseconds, is there any applicability of these elements beside the basic knowledge?
If they don't produce the stable isotopes that they expect to hit at some point, then yeah, the applicability is only fundamental knowledge, yes. But if they are right, and I actually have big trust in my colleagues from physics and nuclear physics especially, I think we could have very new elements which have very different properties. So I'm holding my fingers crossed still.
We have a next question. It is possible that one time we will learn periodic table not in 2D but in 3D or in the higher dimensions?
Yes, there are people also studying the higher dimensional ones. I didn't include this in my talk, but this is also interesting. But it's mostly academic at the moment, because as we know, we are living in a 3D space. Even if we fall back into the realm of string theory, where you have more dimensions, these dimensions are so curled up that it doesn't influence the element. So effectively, we are always in a 3D space.
now we have some kind of personal question, but who is your favorite scientist?
My favorite scientist probably would be my former supervisor from New Zealand, Peter Schwertfeger. So he's a very lively man, and he inspired a lot of what I do today, and I still collaborate with him a lot. So I thank him for actually pushing me to learn new things, and he's a very inspiring person.
Mm-hmm. We have a next question. You have really amazing skills from foreign universities. Why did you come back to your old university?
The implicit, I don't like the insinuation that this is a wrong choice. It shouldn't be like this. I'm usually confronted with this question very often. I think it's not an entirely bad idea to come back, because science is done here as well, and it's done on a very high level. And it doesn't always mean that science elsewhere or anything elsewhere is always better than here. So I'm not so pessimistic about the future of the science in Slovakia.
Mm-hmm. Maybe next question: if theoretically, if we found some new element in the observable universe, should it be places? Should it take place in our periodic table, or we should create some new periodic table like space periodic table?
Yeah, that's an interesting question. But since I don't expect that there will be something which wouldn't fit in our table, like observe something that wouldn't fit in our table, I think we can stick with our model that we have. It will be somewhere at the tail end. So there's plenty of room there still between 118 and 172.
Mm-hmm. I don't see now no more questions here in chat, neither in Facebook. So I think
all right,
we are out of the questions. So thank you very much once again for your presentation.
Thank you for having me.
See you next time.
Bye.
Okay. For other auditors, we will open the official sessions in channels at the 10 a.m. Thank you very much for your coming. Bye.